Let's talk about trapezoids. Okay, this is another method of approximation that we're going to talk about. It is not a Riemann sum. Riemann sums are all rectangular approximations. So this isn't a RAM per se. It is, however, another way to approximate the area under the curve. What we are going to do is, instead of filling our area with rectangles that are kind of, squared off, we're going to use trapezoids. Trapezoids have slanty sides. And so because we're using a trapezoid, we can create shapes that hug the curve a little better. You'll see what I mean when we draw them. And it's going to create a much better approximation for us. So the first thing that we need to talk about is what an actual trapezoid is, because this comes up for me every year. Forgive me if you are thinking, yes, lady, I know this, but this comes up for me every year, so I'm just saying. Most people, when I say trapezoid, picture something like this. That's their shape. Okay, and what we know from geometry is that indeed is, it's a trapezoid, right? So the definition of a trapezoid is that it has four sides. One pair of the sides is parallel. So in this case, that's this side and this side. And one set of sides is not parallel. So look, we're used to seeing a trapezoid like that. People sometimes get confused if somebody draws a trapezoid like this. They're like, that's not a trapezoid. Yes, it is. It has a set of parallel sides and a set of non-parallel sides. The fact that this side is straight up and down means nothing. It's still a trapezoid. Four sides, one set's parallel, one set's not. That's a trapezoid. Okay, now, the reason I bring that up is because the way we're going to draw our trapezoids are even different than how we're used to seeing trapezoids. What we're going to do is we're going to fill our areas. So for example, if I want to fill the area between 2 and 3 with trapezoids, just like I did before, I'm going to mark off my intervals. 1, second interval go from 1 to 2, my third interval go from 2 to 3. And I'm just going to do those ones. Okay. When I draw my shapes, though, again, instead of drawing rectangles and deciding, I'm going to either draw over from the left, or I'm going to start at the right and draw back, or I'm going to draw from the middle, I'm going to draw a trapezoid, and what I'm going to do is connect the endpoints, right? So I'm going to go from here to here and create a shape. Then I'm going to go from here to here and create a shape. I'm going to go from here to here and create a shape. And I've had kids say to me in the past, those aren't trapezoids. They are. The shape I just drew is this. Whoa, goodness. The shape I just drew, badly, but I drew it, is this. One pair of parallel sides and a pair of non-parallel sides. So this is not the type of trapezoid we're used to seeing, and it makes people a little uncomfortable, but it's a trapezoid nonetheless. And so this is the idea. I mean, notice here when I drew, if I filled it up with trapezoids, this idea of extra space and space being left out really shrinks down quite a bit when you are just connecting one endpoint to the next endpoint of an interval. Okay? And you can imagine that if you made your trapezoids even smaller, it would hug the curve even tighter. Local linearity. What? I taught my daughter the phrase local linearity the other day. I'm trying to get her to say it correctly. She's not. She understands the concept, but she cannot say it correctly. Sad. Okay, so look, if I make teeny tiny trapezoids, I'm going to have a bunch of teeny tiny straight lines as tops. Guess what? That's going to create a beautiful curve. That's going to be local linearity. That's going to get you a great approximation. Okay, so look, this approximation method is exactly the same as rectangles, except instead of finding areas of rectangles, we're finding areas of trapezoids. Rectangles are super easy to find the area of, right? Base times height. Trapezoids, the formula is a little more complicated. Not that much more complicated, but a little more. So let's talk about the formula. Okay. When you are finding the area of a trapezoid, this ever so infamous formula is how you do it. So it is half of the height times the sum of the bases. Now, here's how I remember this. Okay. For years, I could not remember this formula until I realized that this is the formula of, you can think of it one of two ways. If you have a trapezoid like this, oh my, this is base 1 and this is base 2, right? Your parallel sides are your bases. If you found the area of this rectangle, that would be base 1 times height. This is your height, even though it's a back and forth measurement. That's a little awkward. Okay. And then you found the area of this big rectangle. That would be base 2 times height. And you averaged them. You added them up and divided by 2. You would have the area. Look what this is. Base 1 times height, base 2 times height, add them up, divided by 2. It's the average if you made a rectangle out of the little side and a rectangle out of the big side. That's what the formula is. The other thing I discovered a few years back when I was trying to simplify this for my geometry kids, came up with this rule for finding areas of four-sided figures. The rule was treat it like a trapezoid. Even if it's a rectangle, treat it like a trapezoid. If it's a triangle, you can treat it like a trapezoid. Check this out. The formula for a triangle is 1/2 base height, right? Okay. That is almost exactly like this. 1/2 sum of the bases times height, except in a triangle, one of the bases is 0. Triangles are trapezoids where one of the bases is 0. So that formula got a lot less ambiguous to me once I figured that out. Okay, so the reason that we write it like this in calculus, because you'll see it 1/2 sum of the bases times height, 1/2 height. I'm going to show you why we write it like this. When we are using trapezoids to approximate area in calculus, what ends up happening, since we are putting trapezoid next to trapezoid next to trapezoid next to trapezoid, the bases, some of them get used more than once. Okay, so for example, this first trapezoid, I'm going to call this, we're going to assume that our heights are going to be all the same here. Okay, this first trapezoid is going to be my height over 2, y0 plus y1, right? That's going to be the area of that green trapezoid. Then I'm going to do another trapezoid right next to it, right? I'm going to try to fill in my curve here. I did a really bad job of making them all look the same width. Bear with me. Okay, so my blue one is still going to be height over 2, except now the sides of this one are y1 and y2. Here's a third trapezoid, height over 2. The bases of this one are the parallel sides, y2 and y3. And we can just keep going, right? Here's another one. My orange one, height over 2. This one is y. Excuse my floating head. Over here. Okay. This one is h over 2, y3 plus y4. And I believe I have one more in here. Oh, no, I don't. Good. Wait, don't look at that yet. All right, so here's what I want you to look at. Algebraically, what happens here, if you simplify this out, I'm going to factor h over 2 out. Again, assuming that our height is the same on all of our trapezoids, which is great, I can factor out an h over 2. And look what happens. y0 is there. There's a y1 here and a y1 here. So you get 2 y1s. There's a y2 here and a y2 here. So you get 2 y2s. There's a y3 here and a y3 here. So you get 2 y3s. And then there's a y4. So I'm showing you this because I want you to notice the magic that happens as long as all of the heights, in other words, your trapezoids have all the same width. you don't necessarily have to calculate individually the area of each trapezoid. Because what ends up happening is these side lengths, for example, in this example, the interior ones, y1, y2, y3, get used twice. So y1 is a base for two trapezoids. It's a base for the green one, it's a base for the blue one. So it shows up twice in our formula. Y2 is a base for two trapezoids, for the blue one and for the pink one. It shows up twice in our formula. Okay. Now, you may like this little shortcut, or you may say, you know what, I'm just going to find the areas of all my trapezoids individually. I'm good to go. Okay. But I want to show you where this formula comes from, because when you look up trapezoidal approximation in a book, the formula that you see that I already accidentally clicked forward is this. And the first time I saw that, I was like, what the heck is going on in my life? And it took me a minute to figure out what they were doing here. Okay, so what they're saying is, okay, provided that your trapezoids all have this same width, which for a trapezoid, we're calling that height, because the height is always just the distance between those parallel sides. And in our case, our parallel sides are the up and down sides. Okay. All you need to do is take the height and divide it by 2, okay, and then add up all the bases. But you are using the interior bases, the ones that got used twice. You're adding those twice. So notice here, this is your first base, the one that started it all. This is your last base, the one that ended it, and then all of the ones in between get doubled. That's all that is saying. Okay? You could ignore this formula and just say, you know what? I'm going to do them individually. I'm going to take y0 plus y1, multiply it by height, divide it by 2. Write that number down. Do y1 plus y2, multiply by height, divide by 2. Write that number down. Go through, find them all, and then add them up. Do it. If you like shortcuts and you're a memorizer, you may want to use this. This may come in handy to you if you have like a lot of trapezoids that you're trying to handle. Okay, let's do an example. I promise this video won't be as long as yesterday's. Okay. Oh, before we do an example, that's right. I wanted to tell you this. Yesterday, I said, before you ask me if MRAM is the average of RRAM and LRAM, I'm going to tell you, don't ask. The answer is no. Guess what is, though? Because remember what I said about the formula for a trapezoid. If you take the average of the rectangle on the short base and the rectangle on the tall base, MRAM and, or LRAM and RRAM, average them out, you get the area of a trapezoid. So if you have your LRAM and your RRAM and you average them, you don't get MRAM. What you do get is trapezoidal. Okay. Now, that's kind of like a handy thing to know. I've not really seen it come up as like a question on the AP. It's not like they've ever been like, well, I'm going to tell you RRAM and MRAM and nothing else, and I'm going to ask you for the trapezoidal approximation. Like, they've got bigger fish to fry, but it's just kind of an interesting fact. And I've noticed over the years that people always kind of assume that that the average is MRAM, and it is not. The average is trapezoidal for that exact reason, it being the average of the short rectangle and the big rectangle. Okay, now we'll do an example. All right, so it says use the trapezoidal rule or trapezoidal approximation, not a RAM. Some people call it TAM. With n equals 4, in other words, I want 4 trapezoids to estimate the area under x squared between 1 and 2. All right, so I'm going to put my head. Okay. Over here. Oh, okay, there we go. Okay. Well, that's not working out. Okay, so I want to go from 1 to 2. And I want 4 intervals. So from 1 to 2. And I want 4 intervals. So look, 1, 2, 3, 4. I see a nice height that I can use. So if I go from 1 to 1 1/4, 1 1/4 to 1 1/2, 1 1/2 So 1.75 and 1.75 to 2, that will get me 4 intervals. So if I do that, the heights of all of my trapezoids will be, whoops, don't! Gosh. I do so much unintentional clicking with online teaching. I feel like I ruin all of my surprises. Okay, so all of my heights are going to be 0.25 or 1/4, right? So when I come in here and I try to draw my trapezoids, my first trapezoid is going to look like this. And notice how tightly this thing hugs the curve. Okay. If I want the area of that, that's going to be this height right here, which is, using our function, 1 squared, plus this height right here, which is 1 1/4 squared. So 1.25 squared. So base 1 plus base 2, and then I'm going to multiply that by 0.25 over 2. It's going to give me my area of that first blue trapezoid. My next trapezoid is going to go from 1.25 to 1.5. And again, look how nicely that kind of hugs our curve. So on the left-hand side, my base is going to be 1.25 squared. And please don't mistake this. This looks a little bit like I'm using the Pythagorean theorem or something. I'm not. The function is x squared. So if I want this y value right here, that's 1.25 squared. If I want the y value right here, that's 1.5 squared. That's what this is. So base 1 plus base 2, and then 0.25 over 2, height over 2. All right. Third one is going to go from 1.5 to 1.75. So again, my first base is 1.5 squared. My second base is going to be 1.75 squared. And then I need to multiply that by the height over 2. So in this case, I am using, for sure, the one at a time method. And in a minute, we'll talk about what it would look like if you use the shortcut method. Okay, here for my last one, I've got a base of 1.75 squared and a base of 2 squared. So 1.75 squared and 2 squared times my height, 0.25 over 2. All right. So again, if you want to, for individual calculations, do the calculations, add them all up. That's fine. There's no reason you can't do that. Okay. If you want to use the shortcut, all you have to do is say, okay, they all have the same height. So first of all, verify that you have even intervals. Okay. So my formula will then start with my height divided by 2. And I'm going to open a big fat bracket. Okay. My first height, f of 1, only got used once. 1.25, that number, this height right here, got used twice. Once for the blue and once for the purple. So 2 times 1.25 squared. This height right here, 1.5, got used twice. Once for purple and once for green. So 2 times 1.5 squared. Plus, this height right here, the 1.75, got used twice. Once for green and once for red. So 2 times 1.75 squared. And then last but not least, this height right here only got used once. So plus 2 squared. And we end it. Now it is worth noting that on the AP exam, that is an acceptable answer. Because they don't make you simplify. So if you were on an open-ended and they asked you to do this problem, you could write that right there and circle it. Obviously, I'm not going to do that. What I'm going to do is pause while we all chug this into our calculators. Did you do it? Did you put it in your calculator? Or did you just wait for me? So when I put it into my calculator, I got 2.34. I'm going to write this down. I got 34375. That's what I got when I added all those numbers up. And since I did a spoiler earlier, we know that the actual value is 2.3 repeating. So that's the actual real area under that curve. With only 4 trapezoids, we got 2.343. That's not too shabby. We were accurate to within a tenth. And darn close to being accurate to within the thousandth. With only 4 intervals. Okay. So trapezoidal is a pretty darn good approximation method. Now again, it is not a Riemann sum. Riemann sums are going to be what carry us forward, but it is an approximation method and worth having in your calculus tool belt. Okay, any questions that you have on the trapezoidal method, pop at the end of this, and I will see you tomorrow. Bye.